The study of a fluid in motion is defined as fluid dynamics. For example, consider water flowing from a tap. The water column from the tap is smooth as the water begins to flow out. As the water descends from the tap, its speed increases and it eventually loses the smoothness of the flow. To understand why the smoothness of the flow of the tap water changes, we need to understand the fluid's motion at the particle level. The path taken by a fluid particle in its flow is called its line of flow. The direction of motion of the particle is given by the tangent at that particular point on the line of flow. Fluids can flow steadily or turbulently. The flow of a fluid is said to be steady or laminar if all the particles passing a given point maintain a steady velocity at that point. The velocity of a given particle may vary from one position to another in its path, but at a given point in the path, all the particles passing through the point have the same velocity. Each particle follows the same path taken by a previous particle passing through that point. The path taken by a fluid particle in a steady flow is called a streamline. The motion of the entire fluid can be represented with a number of streamlines showing the direction of flow in different areas. Thus, steady flow is a streamlined flow. As the tangent at a point in the streamline indicates the direction of motion of all the particles at that point, no two streamlines cross each other. Consider an area in a fluid in a steady flow. All the streamlines that are drawn from the periphery of the area constitute a tube for which the chosen area is the cross-section. Such a tube is called the tube of flow. As the streamlines do not intersect, fluids flowing through different tubes of flow do not intermix even though there is no physical partition between them. Fluid dynamics can be better understood taking into consideration the following three factors studied along with the concept of tube flow. They are incompressibility of liquids, rotational aspect of fluids, and viscosity. Liquids are largely considered incompressible when compared to gases, as they don't change volume in response to pressure as gases do. When the fluid flow is along a straight line, it is called irrotational, whereas when the fluid swirls, the fluid is called rotational. The viscosity of a fluid is related to the internal friction when a layer of fluid slips over another layer. In a non-viscous liquid, the effect of friction is neglected. We have learnt earlier that a fluid flowing through a tube of flow does not intermix with the fluid in other tubes. This implies that the total mass of the fluid entering a given tube through any cross-section of the tube in a given time interval is equal to the total mass of the fluid flowing out of the tube from any other cross-section in the same time interval. Consider a tube of flow represented by AB with area of cross-section A1 and A2 at the two ends A and B. Let V1 and V2 be the velocities of the fluid at ends A and B. Consider an incompressible, irrotational, and non-viscous fluid flowing in a streamline flow in the tube. To find the volume of the fluid, VA going into the tube with the velocity V1 through the cross-section A in time delta t. Consider a small cylinder of length V1 delta t. The volume of the fluid going into the tube through the cross-section at A is A1 V1 delta t. If ρ is the density of the fluid. The mass of the fluid, MA, entering the tube at A in time delta t, is A1 V1 delta t rho. Similarly, consider a small cylinder of length V2 delta t at the end B. Then, the volume of the fluid VB going out of the tube through the cross-section at B in the same time delta t is A2 V2 delta t. Hence, the mass of the fluid, MB, leaving the tube at B in the same time delta t is A2 V2 delta t rho. As the fluid is incompressible, its density remains constant. As the mass of the fluid entering is equal to the mass of the fluid leaving the tube, we have A1 V1 delta t rho is equal to A2 V2 delta t rho. On simplification, we get A1 V1 is equal to A2 V2. This expression is called the equation of continuity. If we consider various points in the tube where the velocities of a fluid are different, we can write A1 V1 is equal to A2 V2 is equal to A3 V3, and so on, equal to AN Vn. Thus, we can say AV is constant. The equation of continuity is valid as the product of area of cross-section and speed remain the same at all points of a tube of flow. The equation of continuity represents the conservation of mass in the case of moving fluids. So far, we have considered the laminar flow of fluids. In practical or real-time situations, the flow of fluids is not always laminar. The velocity of a particle at a point in a fluid varies with time. In such a case, the flow of the fluid is called turbulent flow. If the velocity of a particle in a fluid crosses a particular value, called critical velocity, the flow changes from laminar to turbulent. Critical velocity is the velocity of a liquid at which its flow changes from laminar to turbulent. The speed or the direction of the flow varies in turbulent flow. Thus, the motion of water in a waterfall or a fast-flowing river is turbulent. In the case of water flowing out of a tap, the velocity of water increases as it descends. Thus, at a particular point, the velocity of the water crosses its critical velocity and the flow of water changes from laminar to turbulent. All fluids possess energy. This energy is due to variation in the height of a fluid from a reference level and the velocity of flow. There are three types of energy associated with an element of fluid in motion. They are pressure energy, potential energy, and kinetic energy. According to the law of conservation of energy, as the total energy is conserved, the three forms of energy possessed by a liquid are interconvertible. Bernoulli's equation, developed by Swiss physicist Daniel Bernoulli, relates all these three energies. Bernoulli's principle states that for a streamline flow of an ideal liquid, the total energy per unit mass remains constant at every cross-section throughout the flow. Consider an ideal liquid of density ρ flowing steadily through a tapering pipe from its wide end A to its narrow end B. Let H1 and H2 be the height of ends A and B from ground level. Let P1 be the pressure on the liquid, A1 be the area of cross-section, and V1 be the velocity of the liquid at end A. Let P2 be the pressure on the liquid, A2 be the area of cross-section, and V2 be the velocity of the liquid at end B. According to the equation of continuity, the total mass of the liquid going into the tube through any cross-section should be equal to the total mass coming out of the same tube from any other cross-section at the same time. If m is the mass of the liquid element crossing per second through any section of the tube, then A1V1 is equal to A2V2, which is equal to the volume of the liquid V flowing per second. This can be expressed as the ratio of mass m to density ρ of the liquid. Let this be equation 1. Since the time considered is 1 second, here V1 and V2 are the length of the liquid element of mass m at ends A and B respectively. Thus, A1V1 and A2V2 represent the volume V of the liquid element at ends A and B respectively. Thus, the work done per second on the liquid element against the force due to pressure at A, which is referred to as pressure energy, is given by P1A1 into V1 is equal to P1V. Let this be equation 2. Similarly, the work done per second on the liquid element against the force due to pressure at B is expressed as P2A2 into V2 is equal to P2V. Let this be equation 3. The difference in the work done on the liquid element in moving from A to B is expressed as P1V minus P2V. Let this be equation 4. This difference in the work done is equal to the total change in the mechanical energy of the element. A part of the change in the mechanical energy is used to increase the potential energy of the liquid element and the remainder to increase its kinetic energy. As the liquid element moves from A to B, the velocity of the element increases from V1 to V2 and the height increases from H1 to H2. Thus, the increase in potential energy of the fluid element per second from A to B is expressed as mgh2 minus mgh1. Let this be equation 5. The increase in kinetic energy per second from A to B is expressed as half mv2 square minus half mv1 square. Let this be equation 6. According to the work energy theorem, work done is the sum of the increase in potential energy and the increase in kinetic energy. Substituting and rearranging the terms, we get the equation as shown. Dividing this equation by m, we get equation 8 as shown. As the ratio of mass m to volume V is equal to density ρ, the equation now becomes P1 by ρ plus GH1 plus half V1 square is equal to P2 by rho plus GH2 plus half V2 square. This relationship holds good at any point in a streamlined flow. Thus, we can say P by rho plus GH plus half V square is constant across all points in a streamlined flow. Therefore, the total energy of the fluid, which is the sum of the pressure energy per unit mass, potential energy per unit mass, and kinetic energy per unit mass, remains constant or is conserved across all cross-sections in a streamlined flow. This proves that Bernoulli's principle holds good for all ideal liquids in a streamlined flow. We can also represent this equation as P plus rho GH plus half rho V square is a constant. Thus, in a streamlined flow of an ideal liquid, the sum of the pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume is always a constant at all cross-sections of the liquid. Bernoulli's principle, however, has some limitations. Bernoulli's principle is applicable only to ideal fluids, that is, irrotational, incompressible, and non-viscous fluids in a streamlined flow. If a fluid is compressible, as is generally the case with gases, volumes do not remain constant, and hence density does not remain constant. Thus, we cannot apply Bernoulli's principle to situations such as this. When the liquid is in motion, the viscous drag of the liquid comes into play, which has not been considered while deriving the expression. When the liquid is in motion, some part of the kinetic energy is converted into heat, but it is assumed that there is no loss of kinetic energy. Bernoulli's theorem has a large number of useful applications and is used to explain a wide variety of phenomena for low, viscous and incompressible fluids. According to Bernoulli's equation, the sum of pressure energy per unit mass, potential energy per unit mass, and kinetic energy per unit mass of a fluid is constant. Bernoulli's theorem helps us to study the outflow of liquids from open tanks or open channels. The flow of liquids out of open tanks is measured using orifices. The flow from open channels is measured using weirs. A weir is a low dam built across a stream to raise its level or divert its flow. The flow from open channels and tanks is due to gravity, and the change in velocity is due to the change in the pressure head. Here, we will discuss the outflow of liquids from open tanks. The fluid outflow from a tank is known as efflux. Torricelli postulated a law to express the speed of efflux from an open tank, which is identical to that of a freely falling body. According to Torricelli's law, the speed of a liquid coming out through a hole at a depth h below the free surface of the liquid is the same as that of a body dropped freely through height h under gravity. Consider a liquid of density ρ in a tank of large cross-sectional area A1. Let the liquid flow out of the tank through a hole at the bottom of the tank of cross-sectional area A2. Here, A2 is much smaller than A1. Let P0 be the pressure at the liquid's surfaces that are open to the atmosphere, that is, at both the cross-sections of the tank exposed to the atmosphere. Let H be the height of the liquid column above the orifice. V1 and V2 be the velocity of the liquid at the free surface and out of the orifice respectively. According to Bernoulli's theorem, P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2, where P1, V1 and H1 are the pressure, velocity and height of the liquid at position 1, and P2, V2 and H2 are the pressure, velocity and height of the liquid at position 2 respectively. As the liquid is exposed to the atmosphere at both the openings shown at positions 1 and 2, the pressure on the liquid at both positions is equal to atmospheric pressure P0. As the orifice is close to the bottom of the tank, H2 is considered 0 and the height H1 is taken equal to the height H of the liquid column between the orifice and the top level of the liquid. Thus, we arrive at the expression shown. On simplification, we get the expression shown. Let's call this equation 1. According to the equation of continuity, A1V1 is equal to A2V2, or V1 is equal to A2V2 divided by A1. Let's call this equation 2. Substituting equation 2 in equation 1. And simplifying, we get equation 3 as V2 square multiplied by 1 minus the square of A2 by A1 is equal to 2GH. As A2 is much smaller than A1, A2 in the above equation can be neglected, and hence the equation changes to V2 square is equal to 2GH, or V2 is equal to root 2GH. This represents the speed of a freely falling body, which proves Torricelli's law. The velocity of efflux is maximum when the depth of the orifice is at a maximum vertical distance from the free surface of the liquid, as V is proportional to root h. A venturimeter is used to measure the speed at which an incompressible fluid flows. It was developed by an Italian physicist, G.B. Venturi. A venturimeter is based on Bernoulli's principle. It consists of a tube with a gradually decreasing diameter, which makes a constriction through which the fluid in a pipe is accelerated, followed by a gradually increasing diffuser section that allows the fluid to nearly regain its original pressure head. A manometer in the form of a U-tube is attached to it, with one arm at the wider neck of the tube and the other arm at the narrow point of the constriction. To gauge the speed of flow, the manometer contains a liquid that cannot mix with the liquid flowing through the venturimeter tube. Consider a liquid of density ρ passing through the venturimeter tube with a steady flow. Let ρm be the density of the liquid in the manometer. Consider a point A on the venturimeter tube, where the diameter is larger. Let P1 be the pressure on the liquid. A1 be the area of cross-section and V1 be the velocity of the liquid at A. As the liquid heads for the constriction, the area of the cross-section of the tube decreases, and hence its velocity increases, decreasing the pressure therein. This decrease in the pressure at the constriction creates a vacuum and sucks up the liquid in the manometer limb. Therefore, the liquid in the manometer limb connected to the constriction rises. Consider a point B on constriction. Let P2 be the pressure on the liquid, A2 be the area of cross-section, and V2 be the velocity of the liquid at B. According to the equation of continuity, the total mass of the liquid going into the tube through any cross-section in a given time interval should be equal to the total mass coming out of the tube from any other cross-section in the same time interval. Let m be the mass of the liquid element crossing per second through any section of the tube. Since the time considered is 1 second, here V1 and V2 are the length of the liquid element of mass m at positions A and B respectively. Therefore, A1 V1 is equal to A2 V2, which is equal to the volume of the liquid V flowing per second. As the vertical height of the liquid element flowing through the tube is constant with respect to a reference level, we have H1 equal to H2, and hence Bernoulli's equation takes the form as shown in equation 3. As the velocity V2 is greater than velocity V1, we have pressure P1 greater than pressure P2. We then rearrange the terms in equation 3 to find the difference in pressure at A and B and express it in terms of the density of the liquid and the velocities at the 2 points. From equation 1, A1 by A2 is equal to V2 by V1. Substituting this for the ratio of velocities in equation 4, we get equation 5 as shown. The difference in the pressure at points A and B can be measured as the difference H of the liquid level in the 2 arms of the manometer tube. Thus, the pressure difference is equal to H rho mg. Let this be equation 6. Equations 5 and 6, we get equation 7 as shown. Simplifying equation 7, we get the expression for velocity V1 as shown in equation 8. From equation 2, we get the volume of the liquid flowing per second through the venturimeter at A as equation 9. Simplifying this expression, we get the expression for the volume of the liquid flowing per second through the tube as shown. The principle behind the Venturi meter finds many applications. The carburetor of an automobile has a Venturi channel or nozzle through which air flows at high speed so that the pressure is lowered. The petrol is sucked up into the chamber to provide the correct mixture of air to fuel, which is required for combustion. Other devices that work on this principle are aspirator pumps and sprayers used to spray insecticides.